Hi, I'm Kate Woodland. This is Black Hole Lab 3 for Physics 2211. This lab has two separate parts. The first part will focus on finding the mass of the black hole. We are told the mass of a star located near the black hole, so we know the force of gravity will be a main component in this experiment. We were also told the net force of the star is due solely to the black hole. We can use the fundamental principles about net force combined with the gravity force to solve for the unknown mass. The second part asks us to find an initial launch velocity that doesn't result in the ship crashing either the black hole or with the planet. For this, we will use the mass we found in part 1 to find the net force on the ship and the net force on the planet. We will use the velocity update formula using the new net force to find the final velocity of the planet and the ship. These velocities will be used in the position update formula to find the final positions of the ship and the planet. If at any point the ship is the same position as the planet or the black hole, the ship has crashed and the mission failed. Newton's second law will be a major concept used in this lab. We know that the net force is equal to the rate of change of momentum. We also know that the net force is the sum of its parallel and perpendicular components. The change of momentum is also equivalent to its parallel and perpendicular components, but these can be written differently. The parallel component focuses on any changes in magnitude, while the perpendicular component shows changes in direction. We can set the rate of change in momentum equal to the force of gravity because that's the same as saying F net equals Fg. With some rearranging done through basic algebra, we can create an equation that solves for the mass of the black hole. G represents the gravitational constant, which is equal to 6.7 times 10 to the negative 11th. We were told the mass of the star was 2 times 10 to the 30th kilograms. The lab also told us to make delta T equal to 1 day. 1 day is equivalent to 86,400 seconds. The initial and final velocity equations were given to us. I found the initial and final momentum equations of the star by using the star's mass and its initial and final velocities. This comes from the equation P equals mv. Whenever you are finding the change of something, you must do final minus initial. So that's what I used for the change in velocity and the change in momentum. Again, the rate of change in momentum is the change in momentum over the change in time, which is equivalent to F net. Here we are separating the momentum into magnitude and direction by stating what p hat is. This allows us to write dp over dt in its parallel and perpendicular components. Once we find the parallel component, we can do the total dp over dt minus the parallel one to find the perpendicular component because dp over dt is the sum of the parallel and perpendicular. Everything we just calculated can be put into the mass equation we created previously. This computational model spits out several potential values of the black hole's mass. I put all of these values into Excel to compute the average, which came out to be 1.77416 times 10 to the 34th kilograms. This model also gave us the values for F net and its components on the star. Potential error in this lab comes from that the system outputs multiple values of the black hole, and I took the average of them to find one value. I could have ran the program for a longer period of time to calculate a more accurate average mass. F net force and the rate of change of momentum are equivalent mathematically. That is why we are allowed to manipulate the two equations to be equal to each other and to things equivalent to one or the other. Conceptually, they are slightly different. F net is the sum of all the forces acting on the system. This is sometimes hard to observe because we can't always see every force. The rate of change of momentum can be found by observing initial positions and final positions or initial and final velocities. The rate of change of momentum is focused on how the forces acting on the system are affecting its position and velocity rather than focusing on the forces themselves. For part 2 of this lab, we were told to use the black hole mass we found in part 1. We were also given the planet's mass and the ship's mass. The ship's initial speed components were found through the guess and check method until a model was found that accurately represents the goal of the lab. First, I calculated the force of the black hole on the planet. To do this, I wrote an equation for the displacement between the black hole and the planet. I also found the magnitude of this r vector and r hat. Lastly, I wrote the force of gravity on the planet due to the black hole using the values I just defined. The same process was done for the force of the ship on the planet. To find the net force on the planet, I added the two forces I just found, one from the black hole and one from the ship. The same process is done to calculate the net force on the ship. First, we find the force of gravity due to the black hole. Next, we find the gravitational force caused by the planet. Then we add them together to find the total net force on the ship. With the net forces we just found, we can plug them into the velocity update formula. Then we can plug those velocities into the update position formula. This gives us the location of the planet and the ship after a certain amount of time, allowing us to determine if the ship will crash into anything. The ship is represented by the purple line and the planet is represented by the cyan line. The planet appears to be in a circular orbit around the black hole, but the ship gets pulled really close and then shoots off in the opposite direction. Its path could kind of be described as a slingshot. The ship is long gone before the planet would reach that location of its orbit, so the ship will not crash into the planet. Potential error for this is that to calculate the initial velocity of the ship, I used the guess and check method until I found a velocity that worked. There could have been a more accurate velocity of the ship that I did not try. To get the ship to orbit the black hole, I would need to change the initial velocity of the ship, so the speed in which it left the planet. This would be done through trial and error again. I would also increase my time frame so a full orbit could be completed by both the ship and the planet. From the previous calculations, the model told us that the planet's orbital time was 1.6 hours, so the time period would need to be at least 1.6 hours. This lab showed us how we could find different values by manipulating Newton's second law. This lab also helped clarify the connection between F-net and the rate of change of momentum. Finally, this lab showed us how we can use the net force to find an object's final velocity and position.